Okay, so today I'm going to be talking about the board in MS-14 that's primarily used for pre-charging the motor controllers and for interfacing with the motor controllers. I have the date wrong. I'll change that after. But basically, what we'll be going over is what pre-charging is, what a pre-charge circuit is, the logic behind pre-charge, since that's the majority of the board, and also just the board architecture, so where all the voltage sources are and whatnot. And then finally, I'll go a bit into motor controller CAN. The hardware behind it is not too in-depth, but it's pretty important. From MS, I think it was like 11 to 12, they made a pretty important decision on how to run that, so I'll be going over that as well. But first off, what is pre-charging? What components do you use? What is it for? Is it common, etc.? So basically, the motor controllers have a capacitor across the DC bus input, and it's used to regulate motor current and also ensure that there's no sudden drop in voltage or anything in case your battery gets cut off and whatnot. But if you connect your batteries directly to the capacitors, there's going to be a ton of inrush current if it's just if you just connect a wire short without any resistance. And so if you imagine our battery is 150 volts, capacitors, they're just starting off at 0 volts. You'll have stupidly high current across arcing. You'll probably weld the motor contactors shut, and you'll, in general, be very sad. Motor contactors are just high current relays, for anyone who doesn't know. But yeah, so the capacitors on our motor controllers are 270 microfarads, so they're pretty small. And what you can do is you can calculate what resistance you need using a time constant. So kind of just based on how long you want your pre-charge to take. Ideally, you want to spend as little time as you can pre-charging / discharging, because that's time you can be spending moving. Of course, it's in like the seconds, so it's not that big a deal, but this is something to keep in mind. But the faster so if you want faster pre-charging, you would lower your resistance. But again, the lower the resistance, the higher the current, the more energy you're going to need to convert to heat. So you have to watch out for that as well. But here are some graphs Micah Black made quite a bit ago when we were thinking about the resistance to use. So the way you pre-charge / discharge a circuit is you use power resistors. So these are just resistors that are basically built to convert lots of energy into heat and not die from the heat. And they tend to have high surface area or a plate that's very heat conductive to quickly disperse or dissipate that heat. So if you notice, these resistors are much larger than your typical resistors. They usually come in power ratings of 10 to 100 watts, where your typical resistor that you see might be 0.1 or something. And if you look at the bottom left picture on the flip side, I probably should have gotten an image of this. It's usually a metal pad, and you would have that resistor lie flush against the heatsink, so you can see on the right. And when it lies flush, the heatsink the heat will dissipate into the heatsink, and heatsinks are made with large surface area, so that there's a lot of surface area contacting the air. If you have proper ventilation, this will dissipate heat much faster than just having the resistor. Otherwise, the resistors will still get super hot, and yeah, it's not a good thing. Although in general, pre-charge, it works on a pulse, where if I go back here, you see that the current, the power drops pretty fast in a very small amount of time. So usually it's okay, but things to keep in mind. If you run at high power for a long time, your resistor will burn up. These burn up better, but still you always need proper heat sinking. And so what a pre-charge circuit is basically before you connect the capacitors or any capacitive load to your battery, directly, you run through a different path with high resistance. And once you bring the capacitor's voltage up to a 90–95% of the battery voltage, where since the difference is much smaller, your current won't be as high, then you can change path to the direct path, not through the resistors. since you don't want to run through the resistors all the time because you're just losing energy and you're being inefficient. So it's basically two paths. And the moment you finish precharging, you switch paths. And also in the image, you'll notice a fuse. That's for safety. You should always have that. So yeah, so precharge logic. Is there something? Precharge resistor in the bottom right corner, does it act as a heatsink as well? So bottom right corner, this is the heatsink. This is a heatsink built for TO like 22s. So basically the resistor on the bottom left is supposed to lie flush against this. Like this will just, if you've, I have a picture of the of MCI board later, you'll see what this is, but it's basically, it's not a resistor, it's just a heatsink on the bottom right, and you put the resistor against it. Oh, I have the board right there. Okay, so precharge logic. The way we do precharge is mostly through hardware. There's very little to no firmware involved. Firmware mostly just kind of reads readings to make sure everything's going okay. But basically, this is the board. So you'll notice at the very top, there's a really large white object. That's the heatsink. And you can see the power resistors lying flush against the heatsink. Those are the big resistors where the current will run through. And as they heat up, the heatsink will kind of draw in their heat and dissipate over a larger surface area. But basically, the board itself has a top and bottom half. The top half is where the high voltage line goes, and the logic for the high voltage line. You always want to keep your high voltage stuff kind of isolated from the low voltage stuff so you don't fry everything, like in case something goes wrong. But yeah, you can notice the power resistors. There's also MOSFETs that are really large here. You see two on the left, the TO263s. There's one on the other side as well, plus one on the right, which is for discharging. I'll talk about that later. But same thing, the FETs are really large, meant to be able to take in a lot of power. And then you can see some circuits below that, but still on the higher side. That's for logic for the high voltage line. And then on the bottom side where you see the controller board, you see a lot of connectors. This is the low voltage side. And yeah, the two are isolated. So we can start with the connection from the, oh, is there something in chat? Where is this bottom right corner? Which way is the board oriented? Heatsinks work better if the bar things on heatsink are positioned vertically. This is just face up. I'm not really sure what you mean by which way it's oriented, but
like if the, I don't know what to call those jagged things on the heatsink.
I think they're called fins.
Fins, aren't they more, don't they work better if they're positioned vertically?
I think so, but it kind of depends how you're running your ventilation.
Okay. Oh, is there a fan or something?
There will be fans. I don't know if we'll need them to be running all the time, but we will have fans. But I think in general, if this is inside the battery enclosure, then as long as you have ventilation and like the air is moving, it should be fine. I think you're correct that in general, fins vertically are better, but there's fins on both sides. So this is kind of made, I don't know, I'm pretty sure it's fine. There's probably ways to optimize like airflow, how we like direct airflow with the fans and whatnot, but for now, this is what we have. Maybe I should look into that. But
Nita, you are correct that fins vertically are better when you have natural convection only, so no forced airflow. Yeah, as James mentioned, in our case, we have air moving through the rear electronics enclosure. So those fins are oriented in the direction of the airflow.
I see, okay.
I should double check that in the CAD for the enclosures, but that's the point. Yep.
Okay, so here you see the high voltage in, it goes through fuse, and then it goes to two MOSFETs. These FETs are P-channel, so they are normally on. And if I go back a bit, these are the FETs on the left. They're power FETs, so they have high voltage and power ratings as well, since they're working with the battery voltage. So basically, when a negative voltage is applied to the gate, basically the bottom bit that's cut off, I'll talk more into that later. But when you apply, or not a negative gate source voltage, so compared to the battery, when that's a lower voltage, it'll be open. But as you can see from the high voltage, it connects both to the gate and the source at the moment. So this is normally closed. And basically, we want normally closed, normally on, because we want Precharge to start the moment the car kind of turns on and the boards turn on. So yeah, car turns on, boards turn on. This switch is immediately closed, and the Precharge process will start. And the FETs are just in parallel because I think it's something to do with balancing, helps share the load and whatnot. I haven't actually looked too much into it, but I think it's something like that. And the Precharge path, so basically right after these two FETs, it goes to the Precharge resistors here. You see it's 100 ohms each rated for 15 watts. And you can also see on either side of the resistors, there's two voltage dividers. And basically what this is it measures the voltage of the left side, which is the battery, and the voltage of the right side, which goes to the motor controllers. And the resistors in the voltage divider are spec'd so that at 150 volts, N minus, which is the battery side, will be around 9.39 volts, and N plus at 150 volts is 9.84. So basically, when the voltage on the N plus side reaches about 95% of 150, so that's like 140-ish, it will be greater than N minus, and this is used as this is the way we measure the voltage of the motor controller capacitors and how we know the moment that they are at high enough voltage. So yeah, and you can do the math yourself as just an exercise if you want for the voltage division, but it's down there in the note. And basically the N minus and N plus feed into a comparator op amp. So when N plus is greater than N minus, this op amp will output a logic high. In the bottom, there's a graph of what happens if we just do the comparator. You'll notice when it drops, it'll like bounce up and down really hard. So this comparator works with positive feedback, which means the output is looped back to the non-inverting, input, which is the plus. And so this makes it so that this just provides hysteresis to the circuit, so it doesn't do the bouncing thing you notice in the bottom graph. But once again, when N plus becomes greater than N minus, it means that the motor controller capacitors have reached 95% of the battery voltage of 150 volts. And just on a, if you zoom out a little, this comparator goes to an AND gate, and the AND gate's second input comes from, you'll also see it's N plus. Basically, the reason that this is done is because when the board is off, so when we're not connected to the battery, when we're not connected to 150 volts on the battery, N plus might still be greater than N minus due to just like noise and the way the voltage dividers are set up. And you might accidentally get a logic high even when you shouldn't be. So the way we make up for this is that we run through an AND gate. And I'll show you the graphs later. It makes a lot of sense, actually. It's really cool. But on the AND gate, we also take the measurement from N plus. And just really quick, N plus goes into an N channel, which then goes into a P channel. Yeah, it goes into an N channel and then a P channel. If you imagine that when N plus is logic high, when it gets like the 9-ish volts, the N channel will, actually, wait, this is when I can do the thing. So, yeah, this is the circuit on the bottom half here. This is basically this is the bottom half that goes to the AND gate here. And the top half is the comparator. N minus, you'll notice, is this one. I just have a test point down here just to like show. Or no, that's N plus, and this is N minus. So you'll notice when N minus is at 0 and N plus is at like some low number, maybe N minus is also at that low number, you'll get a logic high out of the comparator, which we don't want because technically nothing's on. So Precharge isn't complete or anything. And then also when I have in minus at about 9.4, that's the 150 volts from the battery. And I turn in plus up until about that much. You'll notice we get a logic high on the comparator as well. And on the bottom half, this also sends a logic high to the AND gate. So the AND gate knows that for sure Precharge is complete. Just to showcase how the bottom works with the FETs kind of chained like this, so you'll see the first N channel is open since there's no voltage at the gate. So the second N channel is experiencing, or the second P channel is experiencing 12 volts at the gate, and so that's open. By having a voltage at the gate of the first N channel, this shorts the circuit, which makes it so that the gate of the P channel is essentially 0 volts, and that shorts that, which sends the 12 volt signal to the AND gate. Did I get that right? I'm sure it's something like that. I have a link in the thing if you want to play with the circuit, but that's basically why there's an N channel and a P channel before it goes to the AND gate, so that the AND gate is always getting the 12 volts instead of whatever in plus is. Oh, sorry. And so if you notice the output, what you want to pay attention to, first of all, is the bottom capacitor voltage. So you'll notice when the capacitor voltage is basically 0, like we haven't started anything, the comparator output actually outputs a logic high, which we don't want. And then when we start charging, then the comparator output will output logic low because the in minus is immediately at the 9 point whatever volts because of the 150 volts. And so after you finish charging, the comparator output also goes high still. The comparator output goes back high, but that's also the first time the AND gate goes high. So this is basically, the AND gate is the end result that we want, where it only goes to logic high when capacitor is finished. But you'll notice that the comparator output goes logic high when we don't want it to. And the second graph is just the battery side. It goes high the moment we start precharging. And so this graph kind of shows you why the AND gate is there. And then you'll see in this circuit, it's after the AND gate, it goes to an SR latch. And SR latch is basically set reset. You guys, I think everyone here has probably learned about it, so I won't go into it. But basically, this is an IC that we use that has actually 4 inputs and 4 outputs, or like 4 set reset inputs, 4 outputs. We only use 1, so we can probably simplify the circuit, but at the moment, it's how we latch our output. Basically, what happens is when the AND gate sends a logic high, the latch will continuously output logic high, even if we like shut down the AND gate. We take away the 12 volts that it's getting, which we will do later on. Also, you'll notice the pin R4 is the reset pin, and that's connected to 12 volts with a capacitor. And basically what this does is that you'll start off with a reset high, because you generally don't want double logic low. It's nice to just know which state you're in. If you look at the truth table on the bottom, double logic low is no change, but you don't know what your previous state was. So what happens is, since the capacitor takes a bit of time to charge, reset will experience a logic high. You'll go immediately into 0, 1 for set reset, and you'll stay at that point until reset will go to 0, but you'll be at 0, 0, no change after first setting the state to be reset. And when the AND gate sends the logic high, then you'll be 1, 0, and you'll be in the set state. And then this will just latch that state. And so that goes to ISO latch out. So that's coming out of Q4. And then the IC after that you see is an opto isolator. What this does is it lets you send a signal without actually connecting the circuits, and it's done optically, so through a light signal. But what happens is when ISO latch out comes out, or when ISO latch out is a logic high, it comes to a N-channel MOSFET, and that shorts the connection of the cathode pin, which on the opto isolator you see CAT. That shorts it to ground. That completes the circuit for the anode cathode from the 12 volts to ground, and that sends a V out latch out. Latch out basically just sends the VCC voltage, which is 12 volts, and so we go from So the SR latches a logic high, and when it does that, the opto isolator will basically continuously send the logic high, but this will send it to the non-isolated side. And that's kind of how we do our isolation. And so you'll notice also there's a signal for ISO latch out before the opto isolator. Sorry, what's up? That's how many pins yeah, so we could probably replace the SR latch with a much simpler circuit. This is, I think, they probably just found an SR latch, was like, that's the job. It's probably way too big on the board for what it does, and it's not particularly useful. It just gets the job done. Like, one of the things Taiping told to me when he handed off the board was like, if you want a task, look into simplifying this. It doesn't really matter too much, but it's another thing that can be done. I think James Joe has taken over the task or something. It's in his Jira. But yeah, it's probably just a little inefficient to have such a big IC for just the use of an SR latch. It just happens to be the one that they found for MS-12, and I haven't bothered to look into it too much to change it. Also, I didn't mention, but there's an enable pin that just enables the latch. Yeah, so you're correct that it's probably not a great reason to have such a big IC with so many unused pins. We just haven't really looked into changing it yet. Yeah, so the ISO latch out, this goes into a circuit. So I showed this earlier with the two P-channel FETs that act as a switch connecting the battery to the pre-charge resistors. But how we control that is through the ISO latch out circuit. And so this first goes into an N channel and then a P channel. So you can imagine when ISO latch out is logic high, it shorts the N channel, which shorts the P channel to the ground, and that will close the two power P channel MOSFETs at the top, which will open the circuit, and so it disconnects the battery. And how this works, I think it's easier to just show, so I will. Let me go to the next tab. Okay, so this right here, this is ISO latch out. This voltage slider, which I can change. And you can imagine this 150 volts is the battery. This 1K resistor would be like the pre-charge resistors. It just goes to ground because I didn't want to draw out the rest of the circuit. But you can see right now that it's similarly in this circuit, the 150 volts is connected both to the gate and the source. Is it the source of the drain? I think it's gate source of the FET. And so I have a test point here. The gate is 141 volts, whereas the source is 150 volts. So being lower and being a P channel, it's normally closed. This is also the reason why we need power MOSFETs, because it's dealing with such high voltages. But if you turn up ISO latch out, so like if you have a positive voltage, then you can see the first N channel gets shorted. And by shorting the N channel, so you see here test point, this is the gate of the P channel. It's 12 volts from the 12 volt source here. But by shorting the N channel, this becomes virtually 0 volts, which it opens the P channel. So the P channel isn't connected to ground anymore. And so the gate of the top P channel is essentially the same as the 150 volts in the battery. And so this is how you open the switch and stop precharging. So basically, like when precharging finishes, it goes to the comparator circuit, does the whole logic thing, and it automatically opens the switch, which is why no firmware is required for this precharge circuit. And the other thing is also out of the ISO optolator is just the latch out logic, or the latch out output, which is the same as the ISO latch out, but this is on the non-isolated side. And this goes into an N channel, which shorts it. And so the motor contactor ground, when latch out is 0 volts or logic low, motor contactor ground is actually experiencing voltage from the precharge switch, which is just 12 volts. But when latch out comes, the N channel is shorted and motor contactor ground becomes 0 volts. And I think that's basically how the contactor is activated. I'm not completely sure, honestly. maybe I shouldn't be saying this on video, but basically this is how you connect the motor contactor grounds. So simultaneously, when the precharge circuit opens, the motor contactor is closed, and that connects the direct circuit from the battery to the motor controller capacitors. And that's the path without any resistance. You also need to discharge the capacitors. So you'll notice this is the right side of the precharge circuit, where after it goes through the three precharge resistors, here are the 3 discharge resistors. They're essentially the same, but these go down to a N-channel depletion MOSFET. And this N-channel is normally closed. So basically what we want is for the capacitors to always be discharging. The moment we turn off the car, or the moment we turn off the boards, it'll be discharging, because we don't want the capacitors to just hold 150 volts in case we need to work with it, because someone's going to get themselves killed. So the moment the board turns off, it'll start discharging all of its charge. So, and this is done by the N-channel depletion, which connects the discharge resistors to ground. But of course, it'll be done in 10 minutes. Of course, when we're pre-charging the car and we're running the car, we don't want it to discharge. So this is the reason why it's an N-channel depletion. So that, or I'll just quickly go over. So why an N-channel depletion? Depletion mode is normally closed and it opens with a negative gate voltage. And we want to discharge when the car is off, so we can't really use an N-channel enhancement. We also can't use a P-channel, because to open the P-channel, we would have to bring the gate voltage up to 150 volts, which is a kind of a pain. If you saw earlier, we need those like really big power FETs. So the IC you see to the left of the MOSFET is just a DC-DC converter that converts the 12 volts to a negative 12 volts, which causes the N-channel to open. And this is how we basically do discharge. So discharge is automatic, where as long as the board is powered, it won't discharge. But the moment the board is unpowered, discharge happens automatically. So now I'm going to go into a bit about the board architecture, just kind of what powers what on the board. This is pretty simple. We have 2 load switches, both powered by VBAT. One goes to VBAT precharge switch, one goes to VBAT ISO switch. And basically what this means is VBAT ISO switch is the power for the isolated side of the board. So like the op-amp comparator, the SR latch, the AND gate, they all get powered from VBAT ISO switch. Whereas on the non-isolated sides, like the thermistors and the fans and the connectors and whatnot, if it needs a 12 volt connection, they take that from VBAT precharge switch. And there's just 2 enable pins on these load switches that we can control. So basically, this is the architecture. It just lets us split up powering the 2 sides of the board and lets us turn on and off the boards when we want. So for example, we can disable VBAT ISO switch to allow discharge without turning off the board. So we leave the non-isolated side of the board on. So VBAT precharge switch will still be enabled. VBAT ISO switch will be disabled. And so that lets us continuously collect data from, say, the thermistors, or continuously power the fans while also discharging if we need to. And this is just kind of like precautionary, useful scenarios. And the VBAT ISO switch, all it really does is power the isolated DC-DC. Since the load switch is still on the non-isolated side, the isolated DC-DC, what it does is it just converts the voltage to the, not converts, but like, it basically supplies the isolated side. And you'll notice on the board where it sits, it spans the gap between the non-isolated side and the isolated side. So this is where the isolated side gets its ISO 12 volts and ISO 12 volt switch. ISO 12 volt switch is also used to power, so if you notice in the bottom schematic, on the right of the opto isolator, you see VBAT precharge switch. All that stuff is powered by the first load switch. All the stuff on the left is powered by the ISO load switch. But you see some of the components are powered by ISO 12 volt switch versus just ISO 12 volts. And that's because when we're done precharging, we can safely turn these components off. We don't need to power those. So what happens is ISO latch out, which is high when precharge is done, that goes to a, I think it's a P channel? I'm forgetting all of a sudden. Yeah, oh, yeah, it's on screen. Yeah, that goes to the P channel. And basically that will drop ISO 12 volt switch to 0 volts. And so you stop powering the comparator and the AND gate because you don't need to, and you save a bit of energy. And anything that needs to stay powered is just powered from ISO 12 volts, which is directly from the V out pin on the isolated DC-DC. And so this is how we power the isolated side. The rest of the circuit is just typical applications, a lot of decoupling capacitors and whatnot because it's a DC-DC. So then the last part of the board is motor controller CAN. And this is basically how we communicate with the motor controllers because they also communicate through CAN. So I think in the olden days, we just had one CAN bus, but since the motor controllers that we buy are a specific product, they have their own defined CAN protocols. And so by sharing one CAN bus, we kind of lock our protocols to the same as the motor controllers. And so the solution that was thought up for MS12 was just have two separate CAN buses. So basically our boards all connect with one CAN bus. The MCI and the motor controllers, so the motor controller interface and the motor controllers have their own CAN for communicating, and the motor controller interface will facilitate the communication between the two CAN buses, so that by having these two separate CAN buses, we can keep our own system CAN and define our own protocols and whatnot. And so we don't have to structure our code around what the motor controller wants. Also, in the past, it means our system, our CAN bus was just flooded with a lot of information from the motor controllers. And since we have a very limited amount of data we can process at once, we would not like that. And so the way we do the two separate CAN buses is with an external CAN controller. And this basically is just an off-the-shelf CAN controller, the MCP2515. This connects to the rest of our system. It connects to our circuit, our controller board. And you can see the pins on the left are just your basic SPI pins with 0 clock, master out, slave in, master and slave out, and chip select. And pins 1 and 2, you see the TX, RX CAN. This is for transceiving and receiving from the CAN network from the motor controller. And so this is just like a sample implementation of the CAN controller where node controller is basically all of our boards, but it'll talk to the external CAN controller, and that will talk to the CAN bus of our motor controllers. So we also have the CAN transceiver because we need to connect to the motor controllers. You'll notice there's the CAN high, CAN low line for the motor controllers. And pins 1 and 4 is CAN transceive and receive. This is connected straight to the previous CAN controller. So pins 1, 2 here, go to pins 1, 4 here. And so this is kind of just how we communicate with our CAN bus. And yeah, so this is basically how MCI, or how we interface with our motor controllers. I think I accidentally deleted the questions slide. So end of presentation. Any questions? Hello?
Yeah, we can hear you.
Well,
yeah.
Let me know if there's anything I should go over. I was kind of talking really, really fast because we had the thing at 3 o'clock, and I wasn't sure how long this would take.
I think it was really well said, James, and I really liked your simulations.
Honestly, the simulations were half for me because remember back in December when we were trying to figure out the transistor logic and stuff? I was just kind of refiguring everything out to make sure I knew why it was an N channel into a P channel, or why it was a P channel to P channel, and all that. So yeah, simulating is really helpful. I do have the I do have the links to the simulations at the bottom here if you ever want to.
That's awesome. Yeah, it's amazing. Cool.
Yeah, sliders lets you, so this one's for comparator. Lets you see what happens when battery's 150 volts and the thing is slowly pre-charged. When it's done, you see that. That and the other thing. Yeah, you get the point.
Right. Yeah, it's really cool. I'm not familiar with that tool. Did you have to set up the sliders with your own range?
You can have like one terminal voltage sources, and then you just right-click it and you can create a slider for it.
Oh, cool. And you can export this as a link?
Sorry? Yeah.
You can, okay.
You can
that's
export
pretty
as link here. Don't worry,
nice.
you'll learn about it because you guys have 220 and classes are still online, right?
Yep.
Mm-hmm. You'll probably be using those. You can throw test
Okay.
points on. The only thing I don't like is, I don't know, it's kind of ugly, but what can you do?
All right.
Yeah, so that's
Yeah,
it.
does anyone have any other questions?
We have less than a minute, so I'm just going to end it here.
Okay, well, I think that was really well done.